So as I mentioned yesterday, as among the fortunate first batch of Indian students to be taught by Ram, and because when Sauli invited me to this conference, I was overjoyed, because not knowing what I would talk here, I was thinking of talking on something on arithmetic groups. But then what happened was Ram visited Bangaluru for an RMS conference, and I was mentioning some question and telling him about some elementary observations. Of course, he said several years back, I mean more than 10 years back, he and Balu had thought about this already. Of course, he said Magnani was enough to say that let's combine these two and why don't you present it in my conference. Of course, I was chastened and I thought, okay, let me follow what he said. That's what I'm going to do, and it's a good opportunity for me to do this. I only hope that some of the elementary arguments don't cloud or hide the beautiful simple ideas that Ram and Balu have in this. Mostly it's going to be elementary, so I can probably give most of the proofs. And unfortunately, we could not complete this conjecture, but we'll see. Hopefully, we will. So this is a very old classical problem. That Cantor gave this bijection between n cross n and n. N for me always includes 0 also. So this is pictorially you can see this is the one where you follow this path of counting. So this is one of the things, and when you start from the right, this is the one. When you start from the top, go top and this, then there's the other one, which is this fyx. Okay, so I didn't know about this earlier when I had talked to Ram that this is already proved by Fueter and Polya that these are the only two bijections, and they had conjectured that there are no higher degree polynomial bijections from n cross n to n. Okay, so the hope was that we will, there are some ideas which you could use and prove the conjecture in full. I should mention that the original proof by Fueter and Polya uses somewhat deep transcendental methods like Gelfand's theorem and so on, Lindemann's theorem. So as I mentioned, the word quadratic should be dropped. That's what the conjecture says. Okay, so idea is to give an approach to this conjecture and hoping to solve it later, not now. But at least it gives a hold on how to prove the conjecture, the original question of Fueter and Polya, original theorem of Fueter and Polya, I should say, gives another proof of that. So I mentioned some other results. Okay, so I should say. So this is a reference 4, which is by somebody named Maxim Semirnov, who was a student of Matiashevich. He has given also a proof, elementary proof of the Fueter-Polya theorem, that these two are the only polynomials of degree 2. So we are going to give another proof. So I just make some small observations. All are elementary here. So if you have higher dimensions, if you have n cross n cross n r copies, then look at this polynomial function. Okay, so here is a sort of simple proof that this gives a bijection from n power r to n. Of course, there is no question. I don't think there is even a conjecture of what are all the bijections from n power r to n for general r. Okay, so let's look at this little lemma. Look at the polynomial which I claim is a bijection from n to the r to n. So look at this subset of this box of this summation ai less than or equal to t. From this box to the subset of, where is it? To this set of all these non-negative integers, there is a bijection. This map gives a bijection. Let's see why. It's very simple. So we just do it inductively. Okay, the first case is for r equal to 1 is obvious. So start with general r. What happens is this, the range of this fr is just by inductive hypothesis, and look at the binomial coefficient that you are adding here. When you are looking at the box summation xi less than or equal to t, then the range of this is this. The range of the whole polynomial fr plus 1 is at the most, I mentioned here, sorry, at the most this. Now when you look at the size of the set from which your box, then it's just this t plus r plus 1, choose r plus 1. So it exactly matches. So in other words, this map fr plus 1 gives a bijection from this subset to this subset of n power r to n, and when you let t tend to infinity, it gives a bijection from n to the r to n. Okay, so because there is no idea, I don't know if we can of course permute these variables and get other bijections, but whether there are totally new bijections, polynomial bijections, I don't know. I don't think there is any conjecture to that effect. Here is a small little interesting observation. I have an elementary proof here, but it's not as obvious as it should be. So suppose you take one variable, suppose you take a polynomial on one variable, when can it be a bijection? So of course, if it is linear, definitely there are, if it's a linear polynomial, you can always find infinite subset of rational numbers of which it's a bijection. If it's not linear, then it cannot be, is what I'm claiming. Higher degree polynomial cannot give a bijection on an infinite subset of Q. So of course, for degree 1 there is nothing to prove. Let's look at the proof for higher degree. Assume that this polynomial is degree n bigger than 1, and suppose there is an infinite set which it permutes. Okay, now look at the, we just get rid of the coefficient of x to the n minus 1, the top but 1 coefficient, by doing this process. So you can as well assume that the coefficient of x to the n minus 1 is 0. Okay. So write the polynomial in this fashion, summation ai x power I by d, where d is a common denominator. So now the idea is the following. So you have this subset S, fix any point p by q, a rational number in this subset, and since f is a bijection on this subset, you look at, so let's say p0 by q0 is the starting point, this p by q that you have fixed, and look at the images under f and its pre-image under f. That's your sequence pn by qn, where n goes through integers, positive and negative. So the fact that f of pi to the by qi is the next fraction tells you this equality. Okay, and notice that since there is no coefficient of there is no a n minus 1 here, this means in this equality qi square will divide qi plus 1 times a n. Remember, a n is the top coefficient. Okay, f of pi by qi is pi plus 1 by qi plus 1, and say qi square will divide this. So in case qi plus 1 is bigger than mod a n, then we'll have the fraction, the next fraction has higher denominator. So in fact, we can go backwards this way. In other words, we can deduce that there are infinitely many negative k for which this has to be less than or equal to mod a n because of this process. Okay. Once you have this, and the other observation is that if you look at the polynomial from some stage onwards, say mod x less than or equal to m, that is f mod of fx is less than or equal to n, fix such a constant, such constant m and n. Sorry. So we claim that, I think we missed out something. Sorry. So I'm claiming that this sequence is periodic. So what we are going to say is every element is part of a periodic sequence, and each of the sequences has a denominator bounded by a fixed number, which is mod of a n. So there will be it will be a finite set. That is the idea. So let's just see. So look at the sequence. So suppose pk by qk is bigger than maximum of mod mn. Mn is like this. Then since pk by qk is an f value, and it is bigger than, it must be bigger than m. Otherwise, this is happening, right? Because of this. Similarly, actually, we can easily show by induction that f p of not just pk minus 1 by qk minus 1, but pk minus r by qk minus r is smaller than this. Okay, I have just given the proof here. Inductively, it follows. So, as observed, infinitely many negative suffixes are there for which the denominator is less than or equal to mod a n. So, there may exist arbitrarily large fractions like this which are equal. So, you know that once two fractions are equal at a distance, the f values are also equal. So, this will follow that your sequence is periodic. So, since we have an arbitrary element, every element is part of a periodic sequence, and it's your set S is a union of these sets, and each of them has, in the first observation we made was that each of them has a denominator less than or equal to mod of a n. So, this set has to be finite, the numbers are all bounded by that. So, this is elementary, but okay. So this is just one dimension. I just want to make this comment. Coming to this Cantor polynomial, so the idea one has is that if you have a polynomial in higher number of variables, perhaps we should be able to use methods, like for example, Korva-Hazania's proof of using the subspace theorem and so on, right? If you have a higher degree polynomial, perhaps it should be possible to say that your solutions of fxy equal to z, okay. So you want to say f is not surjective if f has higher degree. So fxy equal to z, you're looking at that surface. So you want to say all the points of this integral points of the surface are in some smaller curve or something like that, or union of curves. We haven't investigated as that. So the point I'm trying to say, this method is slightly more analytic, but that earlier comment will be useful if somebody wants to try it out. So let's start with the bijection of degree d. Okay. So write the homogeneous decomposition if d is the highest degree term. So break up the highest degree term into, so over reals you break it up like this. So either things are of this form or this form or this form, where Cj's are also positive, Ek's are also positive. So claim is that these are all, first claim is that these are all even. It's more or less easy by Rolle's theorem kind of thing. So proceed as follows. Suppose some bk is some bi is odd. So take some interval around it ei, so that there is no other ei plus 1. That's what you're going to do. And then so what will happen is this polynomial will have opposite signs at those points. Okay. So that means since this whole thing is positive here, so call height h as maximum mod x mod y, then since these are of bigger than h to the d being the degree, this is the highest homogeneous factor. This is also true for the full f for sufficiently large height. So then you just have to choose y, which is reduced by denominators of the alpha and beta that you chose, which are close to the next. Okay, sorry. Then you get a contradiction because f has to take positive values. I want to say that if b were one of the bi's were odd, you can choose so that it becomes negative at some point and positive at some point. Okay, so here is the thing. So you remember EIs were the, let me go back only once. EIs are this. Let's keep this in mind. These are the negative, so everything else here is positive. Okay, so first claim is that if each of the EIs has this property, okay, then it's really good for us. The point is that then we'll have a lower bound of this kind. Why is that so? It's again easy to see. You remember x minus eiy coming with power bi, and the sum of the bi is e or b. That means this lower bound will imply this lower bound because the whole degree is d, and since the other part is just a smaller degree, you can have this smaller bound, will be done. So the whole thing will be this. What we want, let me go before come to this. What I want to say is that this focus may not happen for all I, but if it doesn't happen for all I, then so it's less than, say x minus some e1 y is less than y to the 1 minus epsilon, then it can happen only for e1. It can't happen for other ei's, obviously, because the size is y power 1 minus epsilon. So we will use that. So strategy now is the following. So if f is a bijection, of course look at the corresponding Dirichlet series, this series 1 by fxy power is with a Riemann zeta function. And what we would like to say is that unless f is something like the Cantor polynomial, if f doesn't have a small degree, this is going to pick up various other poles. So let's see, split the sum on the left hand side, the two sums. So remember the previous lemma said x minus eiy bigger than y power 1 minus epsilon, that kind of. So that is the first sum. Those xy satisfying that is the sum S1. So the nice sum, so to say. So in the former case, we have, because of the bound we had h toward d minus epsilon b, we have this kind of a convergence of this series. Okay. So in the second sum is when the problem is, when this is violated. So, and as I said, it's violated only for at the most one E1, one EI. Okay, it's obvious again. X minus E1y is O to the O of y to the 1 minus epsilon, and also it happens, then difference would be y to the 1 minus epsilon, which is not possible. Okay. So henceforth we will suppose that this is a bad situation. Okay. Otherwise we are done. If all the EIs satisfied the lemma that I mentioned, then we are through. So we will try to explain the analysis sum this thing by trying to get a lower bound on the fxy. Second sum, remember where. So first observation is that if the d minus 1th homogeneous factor, that is the top but one factor of f, it does not have the same x minus e1y as a factor, then also we are in a good shape. First of all, it's positive. Okay. Okay, I'll just mention why it is positive. Since it is bigger than y to the d minus 1, if this is negative, then we can choose something which is smaller than, which is so that f becomes negative. Whole thing is again and again we are using that f takes only positive values. Okay, so if f d minus 1 does not have this as a factor, then fxy, that polynomial bijection, is at least h to the d minus 1. And this is a good situation. Because what, okay, let me just see why this is just by looking at the Taylor expansion around E1y. So look at this expansion, okay, and since this is O to the O of y to the 1 minus epsilon, we get this. See, because this is bigger than y to the d minus 1, the other part just contributes this. Again elementary. Okay, so here I just want to sort of go to a special case. Actually, much more can be said here. For example, B was the sum of the degrees of the factors x minus eiy. So if it assume that say B1 is at least B1 is 2, then this argument works, and some other arguments also. But I'll just consider on this case because this will tell you how to deduce it. If the degree is 2, then the bijection has to be the Cantor polynomial. So let's consider on B equal to 2 case. So there exists so here is a very nice and crucial observation. If x minus e1y is bigger than or equal to c for a large enough constant, then we have this bound. Why is this good? First of all, let's see the proof. So look at the so remember that b is 2. That means when you write f dxy as x minus e1y square times axy does not have x minus e1y as a factor. So that means you have this kind of lower bound, whereas the previous one, we are assuming that we are in the bad situation when this is a factor of this, but nevertheless this is at the most lambda y to the d minus 2. This could have a factor of that. Okay, so that means previous other because the smaller degrees of course are at the most y to the d minus 2, right? So overall, if you just choose lambda large enough, this will dominate everything, and then you will get what is said here, h to the d minus 2 will be the lower bound. So except on this, so we have a constant c, so that when x minus e1y is at least the constant c, we are in good shape. Okay, fxy has the lower bound, and the Dirichlet series will converge for, so this is bounded above by 1 by h to the d minus 2 to the s and so on. Okay, so what we are looking at is only this finitely many lines. If this top coefficient is coefficient of y square or higher, then also we are through, because the Dirichlet series will converge for real part of s bigger than half, whereas it is a Riemann zeta function here, if it were a bijection. Okay, so let's assume that this is of this form. So the bad case is this. So now write this in this form, where this part is nice and it's regular for real part of s bigger than half, as I said earlier. So all the bad part is considered here. Now look at this progressions. Okay, so first of all, recognize this is a sum as a Hurwitz zeta function, okay, which is also known to have analytic continuation and to the entire complex plane, simple pole residue 1. So let's calculate the residues of both sides. Okay, so we have this equality, mk is coming from here, but you see what's happening. What kind of, this kind of arithmetic progression how much does it cover? So when you have y less than or equal to n, this covers something like n to the mk, n by mk plus bounded number. So this can miss only a finite number of terms. You see, that means the sum over S2 can miss over only finite number of terms. Sum over S1 can cover only a finite number of terms if there were a bijection, but we already know that sum over S1 covers infinitely many terms. So for a for F to be a bijection, to be injective, this is contradicted. Okay, so I think this idea has scope to be generalized. Okay. We just took the special case when the sum of the degrees of the EIs x minus EIy is 2. You can take one of the degrees to be 2 and still it works, but perhaps it has much more scope. And since I am going to concentrate on the degree 2 case, which is Fueter Polya theorem, for which I am going to give a simple proof. Let us just look at this. So we are looking at the case when degree is at most 2. These two cases. So let me just write it. Okay, I just want to mention one small this thing. So earlier lemmas we wrote on fd has this factor, fd minus 1 also has the same factor. If it does not have a factor, we are through. If it has a factor, then we are in bad shape, then we are looking at further cases. So suppose if you keep on doing this, if you have this kind of thing, if fd minus 1 does not have this factor, then again we can conclude a lower bound like this, and so we will have at least the Fueter Polya conjecture for high enough degree. So for in this case, okay. So we can push it through, except that it might happen that all the fj's have the same common factor. Then we don't know what to do. It is not clear how to extend, but nevertheless, let us now concentrate on this degree 2 case. Okay. So degree 2 is known case, as I said, Fueter Polya themselves proved it, and this is, and what the above argument shows, among other things, is that this case does not arise, first case. It's very strange. Okay. So first case cannot occur is what we have seen, okay, from the earlier argument. Of course, the earlier argument should really be seen as an approach to the general degree problem. I am just viewing it right now as towards degree 2. What is it saying? So now we have these two other cases, and what we will show is that this case cannot occur, and this case exactly reduces to the two polynomials, Cantor polynomials. Okay, so first thing is that general. So I am not specifying any particular case among the three cases. Any of these cases, look at this polynomial of degree 2, and suppose it gives a bijection. Then we want to say this is never takes the value 0, other than 0, 0. You cannot take. So the homogeneous part I am talking about. Okay. Presumably, I mean, it's possible that it might be 0 somewhere, right? Only f we know something about, but it's. So suppose we assume there is some point where it is 0, and so on the whole positive ray it is 0. Similarly, since f2 is not a 0 polynomial, there is a ray on which it is totally positive. What we want to show is that both of these intersect, and in such a way that f will take the same value on these two rays. That's what we will try to do. Okay, so note that, okay, I just mentioned here why this has to be positive here. Somewhere it is non-zero, but I said it should be positive, just because you can choose S big enough, large enough S. So as I said, there are two common point on two rays which on which f takes the same value. Okay, that's what we would say. Provided f has a, so we assume that f2 is 0 somewhere. So what we want is something of this kind. Remember, xy is the point where it is 0, zw is where it is positive. So we want to solve for this where R and S are both positive. Of course, we want to be in positive. So you want an equality of this kind. Of course, you can just simply set S to be this and R to be this. Of course, we have to make sure that both are positive. Okay. So indeed, S, if you choose S large enough, not S large enough, sorry. Yeah, F1 has to be positive, right? If we want to say F1 is positive, then. See, look at the, so I said R you can choose this and S you can choose to be F1 xy. So we may assume that F2 is bigger than mod of F1 ZW for large enough. Indeed, the original choice did not satisfy, you can just go along the ray and choose something else, right. So once you have F2 positive, and you can choose corresponding R and S. Okay. So the idea is simple. So this is just a general observation that homogeneous part is not vanishing anywhere. Okay, that is not guaranteed. It is. Okay. Now look at the case 2. We want to say that also cannot occur first. Let's make one small little observation. So when you have whenever you have a real polynomial like this, which takes which is a bijection, not only the values, the coefficients are rational, but you can say something like this. Oh, there is a misprint here, I think. This not be b minus c, but c minus e here. So what I am saying is a, c, d, e are half integers and f is an integer, but 2a and 2d are the same parity, and 2c and 2e are the same parity. Okay, that's what it should be c here. Okay, so just by putting special values you can see that, and this will be useful because the proof is going to be simple combinatorics. So look at this polynomial, then I want to say this form cannot be a bijection. So let's see why. Okay, I think maybe I should concentrate on one other proof. This proof, you see, it depends on the following choice of a particular polynomial. Suppose, okay, let me just skip that. This polynomial gives rise to an equation of this form, and you should be able to. The fact that fxy is a bijection will be contradicted if we can choose primes of with certain properties. Namely, for example, if uv is nobody likes to see calculation, but the point is that if you choose a prime which divides, so we'll here an equation of this kind. So let me just show this. So take a prime 3 mod 4 which does not divide this part. So you can always, f will not take all values. F is not surjective, as I want to say in the special case, because it depends very much on this special form of this form of this. Okay, I'll skip this for sure. Similarly, I have another case. So basically, I've said that case 1 is doesn't occur because of earlier argument. Case 2 can argue like this. Case 3 is more interesting because we want to say it has to reduce the Cantor polynomials. So we'll look at this polynomial, this form. See, C1 and C2 are positive. So we want to show this. What do we want to show? That C1, C2 are positive, and A is half, and C1, C2 are 1, F is 0, and okay. So there are two cases when D is, yeah, okay, I put both here. D is 3 by 2, 1 by 2, or 1 by 2, 3 by 2, depending on the. So let's, this will be done in 3 steps. This coefficient of xy, I will say this is the most difficult step, difficult in the sense of combinatorics, is less than 2. And if the coefficient is less than 2, first you can say the homogeneous part is this. And finally, if the homogeneous part is this, we'll conclude this Cantor polynomial. So let's see. First, I have time. So let's look at the proof of step 2, because that is, step 1 is more difficult. I'll just first do the step 2. You want to say if the coefficient of xy is less than 2, then your homogeneous part is going to be x plus y whole square by 2. Anyway, first thing we want is that this polynomial is of this form by its negative definiteness. Look at the coefficient of xy, 2ac, which is less than 2, and which we assumed, step 1 we are assuming. And then this equation simply means that you remember that a is half integer and so on, right? And 2a times 2ac, so these both are going to be 1. That means we have this form. So as I said, the next step is also quite easy. If f2 is of this form, then f is one of the 2 Cantor polynomials. So remember that, see, d and these have the same parity as the coefficient of x square and coefficient of y square respectively. I mean, twice the coefficient of x square and twice the coefficient of y square have the parity of twice of d and twice of e. Okay. So since it is odd here, that means d and e are 2d and 2e are both odd. Okay, and of course they are not equal. Okay, otherwise f can't be injected. So let's assume one of them is whichever is bigger. Let's say d is bigger than e. We'll prove that this happens D is at least this and E is at least that. So that will show that your polynomial, which is bijection, is bounded below by the Cantor polynomial, which is a bijection everywhere. That can happen only if they are equal. So we want to say this happens. So basically we want to say D is bigger than this. And so when you look at this, so I will rewrite this equation like this: A is x plus y b. So just a rewriting of this. I am just writing A as E minus half, the original. So advantage of rewriting like this is that you got actual integers, not half integers. Okay. A, B, C are all integers now. So if B is bigger than 1, this B is bigger than 1, we want to say there is a contradiction to the injectivity. So each step, I mean, maybe you can squeeze out something more, not just bijectivity. Sometimes injectivity you can say if the polynomial is injective, this cannot be so and so on. But I'm not. So look at an arbitrary. Oh, again, there is a misprint. I'm sorry. This C should be B. See, here is your polynomial f, and I want to say that B cannot be bigger than 1. Okay. If B is bigger than 1, look at 0 bt minus a and b minus 1 times t. You see from this, these two are equal. So if t is large enough, where this happens, then we'll have a contradiction of to injectivity. Okay. You see this? These two are equal from here. So we must have okay. So put equal to 1, then you get this, which is also a contradiction. So ultimately, this will reduce to this Cantor polynomial. So let's go to the first step, which is, as I said, combinatorially the more difficult one. Here it was a bit tricky because what you want to say is injectivity is contradicted in the following way. If it's not a Cantor polynomial, what you want to say is that if the coefficient of xy is not less than 2, you will be able to produce some subsets of cardinality bigger, say less than subset of cardinality less than equal to t, so that it goes to something of cardinality less than t. Okay. So if the t is very tricky to choose. Okay. So we are assuming that this coefficient is bigger than equal to 2, and we want to get a contradiction. Okay. So suppose we show that. So here, of course, we are using both injectivity and surjectivity of f. We will say that f is not surjective. So for that, we want to get a t for which the number of fxy less than t, number of xy for which fxy less than t is strictly less than t, strictly less than t minus 1. I put less than here, so less than t minus 1. So you see that your 2d and 2e are some integers. One of them is negative. Otherwise, you are done. It cannot be surjective. Okay, so this is a tricky rewriting of. So I am rewriting your f, okay, in this form. You see, I just subtracted t and so on, writing to different ways. So in case both x and y are bigger and x plus y is also bigger and some other multiple of t, then we should be able to. Then fxy is bigger than equal to this. That's why elementary argument is bigger than equal to u square t square by 2. In other words, if this is less than u square t square by 2, so this here t is anything fixed, we have not chosen t, any possible t, then x is less than t, or this happens. But it's still, this number of these is still quite large, or is still not enough. So you go to the next level, so you take this when both x and y are positive, or bigger than equal to some constant coefficient constant times t, then you get a bound of this form. So you have to take three types of, so in case this is contradictor, you have both x and y less than v of t. The third final this thing is, if you take x and x w t, y is also, or y is bigger than equal to w t, then this kind of bound you get. Now all the three bounds you have to play together with this, you play with all the three bounds together. What happens is you want to choose so that this second bond and third bond are bigger than equal to first bond. So then it's a matter of counting. I just don't want to go too much into it, but you see that certain choice will tell you number of xy. We obtain the number. We obtain the number. Okay, which number is it? I am looking at the number of xy for which this is happening. This happens, and either this or this happens, and this happens. There are 3 bounds you get, right? So when you count that, ultimately it turns out that this number is, this happens. So for that choice of t, so t you can choose something like this. Okay, this is certain number. You can always have this. So as I said, this combinatorial argument is bound, combining together the. Okay, so I just mentioned that this is work of Liu and Rosenberg also goes say something towards the conjecture of Fueter and Polya, but I don't think anybody has done a conjecture about higher degree, and hopefully we should be able to prove it later. I thank you.